at force, and let's go and have a look at some ideas about momentum and the force that might be involved in this. So what I've got is I've got a little track here, and what I've got is this idea that people have. There's quite a few games, and let's just throw a little coin somewhere along there. And how much effort do I need to do to push these coins to be the same as that one? Oh, much more than that. Oh, that was useless. And we've got here quite a friction surface here to try and deal with this. And what's really going on here? Well, I want to look at what's going on. I'm going to have a look at this in an anecdotal way. And what I've done is I've raided my children's Lego track. To be honest, they haven't played with it for quite a few years now. You know, once they passed 18, they didn't seem to want to play this too much. And I've got here a grey and a black one. Let's see what happens if we push this one with a fair speed and see what happens when we go and they join. Well, that didn't work well. Let's put them back on the track. Right, they're better on the track now. Well, did you notice anything? It was quite hard to see. I'm going to move the camera a little bit so you've got a better idea of what's going on with this second train. We're looking at the velocity of this going before it hits the other one, and then the velocity afterwards. Well, can you tell any difference? Well, I'm looking at this thinking, well, I can't tell an awful lot of difference here. So maybe we need to do this experiment in a better way. So let's take this track off, and instead we're going to have a look at some smart carts doing the same experiment. So if we do this without any recording, let's just have a look and see what's going to happen. I'll give this a bit of a push, and I can definitely see that it's a lot slower. How much slower? Well, I suppose what we're going to need to do is to set these up, and let's record what's going on. I have some software here. I've got on here a couple of smart carts, so I'll just get rid of those, and I'm just going to record here a graph. I don't want it. So I don't think I want this at all. It's calling something else up. Right, okay, so no, right, no, oh, right, and we'll tell it to do file new. Right, didn't check that before I started. Let's just call up a graph. And what we're going to do is we can here select the measurement, and let's choose, first of all, we're going to move the blue cart. So let's have a look at the position of the blue cart with respect to time, and let's see what happens with that. I don't want the angular velocity. I just want its position of the blue car. Right, let's move it down. There we go. So we've got some position. Let's have a look and see how its position changes. We're going to have a look at all sorts of things here. So I'm recording its position. I'm going to move it back. This is where it's going to start from. Let's fire. And that's what I've got. We've got one velocity here. So let's look at the velocity, because it's probably easier to look at the velocity. And we can see that I gave it an initial velocity, and that's slowing down, and then it's got a final velocity. And let's see what we've got. So let's just take a little line here. It's not let me do it. There we go. And this is about 0.28 meters per second. That's its acceleration. And let's do another one. Right, I'm not sure what's going on there. Let's do this experiment again. I'll get everything set up way I want it to record. So we're going to look at here. That's better. Now I'm looking at our velocity, and am I seeing much change in velocity? Well, I don't think I am really. I would have liked to have seen that staying at the same speed, and that's not working. So I'm going to need to make some modifications to my track. So let's do that. What I'm going to do is I'm just going to raise these up a little bit. Just going to send them down rather than hanging on to them. And I'm hoping that if I send one of these little tracks along, this should, it's accelerating quite a lot there, so I'm going to lower the track. I'm making a guess at where I want it. And that's accelerating very slightly. Now that's not a bad thing, that if I now push this, it should possibly, the acceleration down should compensate gravity and friction. So let's have a look. Let's just get this right. So I'm going to now set this up again, recording. Let's release it, and that's accelerating too much. So what I'm going to do is I'm going to lower this a little bit just to try and compensate for the friction. Let's try it once again. Fire. And that's slowing down. So I want to speed it up a little bit, so I've got to adjust this again just to bring it up a little bit. And if you turn the cart back, we've got to get it right here. So I've got the system recording. Here we go. Let's now go back. Let's try the cart again. I've got my first cart, my second cart, and let's see what happens to these carts this time. And here we go. Well, looking better. My problem was I didn't have it far enough. I'm not helping myself there. I just adjusted it all. Right, so one cart. Hoping it's more or less going to stay where it is. Let's see if we can try this again. So let's start this. Here we go. And that looks much better. What we've got is a velocity here of about 0.4, and then we've got a velocity here of about 0.2, and that looks like what's happening is when I push the cart, it's got a speed in one direction, and it's minus because it has to be vector, of 0.4. And then when the two carts join together, we've got the value of about 0.2. So that appears to be what we saw with the trains, that when we sent our cart down, it had one particular velocity, and when it crashed into the two, we had a slower or lower velocity. Let's look at what's actually going on. So here we've got momentum. Now momentum is the mass times the velocity. So our units of momentum are going to be kilograms, meters per second. And the symbol for momentum is P. I'm sorry, I don't know why it's P. It's just the way it is. So if we want to work out here, we're going to look at a change in momentum, so we can work out what our mass of our trolley is, and we can work out the mass of our trolley, and we'll get a quick rough and dirty pair of scales just to work out the velocity, the mass of the trolley. And we've got the mass there, and then we can work out the velocity, and the velocity we worked out here was 0.4. So let's work out first of all the mass of the trolley, and this is going to be quite a rough and ready method of doing it, but it will do because our trolley comes in at 277 grams. If I actually took this bit off, which is extra little bit of buffers, which I was using, then this should be about 250 grams. So these are not that far off of 250 grams. So as I said, they're 277, and the mass of the other one 273, so 4 grams in it. So we haven't got much in the way of mass here to worry about, so let's put in our 277 grams. And that we want to turn into kilograms, so 0.277 kilograms, and that is going to be multiplied by 0.4. Let's just do that. So let's put in 0.4 times 0.277, and that's going to give us a momentum of not very much, you see, 0.1108, so effectively just 0.1. So this is our mass times our velocity. So if we look at before our collision, what have we got? We've got our mass 1 and our velocity 1 plus our other mass, and that's going to be here our 0.1 plus the same mass effectively times 0 is going to give me 0, and that's going to equal our new mass and our new velocity, and our new mass is going to be double that, so effectively 500, which is 0.5 kilograms times our velocity, which we worked out from our graph was there about 0.2, and if we multiply those together we get our answer, which shouldn't be that surprising, which is just 0.1. The momentum before the collision has to equal the momentum after the collision. We can see this more realistically if I have a look at two of these carts working at the same time. And what we should be able to do is put in the values for this cart, and I should be able to record also the values for this second smart cart. And let's see if they do indeed tie up. So what I'm going to do is I'm going to start with a new experiment to do this. And to do that we need to file new experiment, and I'm not interested in any of this, so I'll just discard it. And what I want to do is we'll just look up a graph and I can get some data here. The data I want to get here from this is I'm going to record the velocity of the blue cart, and I'm also here going to take the velocity of the red cart. And I now need to remember the right thing to press here to add a new plot. So there's my two graphs. I'm going to have, let's have our blue on the top and let's have our red on the bottom. And let's see if doing the same experiment we get anything intelligent happening. So I've got my blue cart here ready to go to hit my red cart. The red cart will be doing nothing to start with, so let's just record this. At the moment nothing's happening. Let's release the carts. And we can see something happening. Let's try and take a look at this data and see what we've got. At the start, this blue cart is travelling at, and let's get some data in here. I'm going to about there. We can see it's doing about 0.4, just over 0.4, and then this one is doing 0, which is not surprising, it hasn't had a collision yet. Then we have our collision acceleration, and if we look at a time around about there, we'll now see that they're now going off at the same velocity. Now that's not really surprising because the two carts are actually joined here by Velcro. When they've actually collided, they have become one cart. So their mass has increased. So quite a simple experiment. We've got two identical trucks and we'd expect momentum to be conserved. It is, and we expect as the velocity of one basically collides with the other, the velocity is halved to keep the momentum. What happens if the mass is different? Let's have a look at this. One of the things I've got with my little trucks is I've got some masses I can go with this. So let's initially make the second truck heavier. Now this is in fact the weight of one vehicle. It's about 250 grams. Some people get a bit stroppy and say, could you not make it two carts? And I can just shove another cart on top, and that's probably an easier way of seeing what's going on. So I've got a mass of two carts here, and what we're going to do is we're going to get this one cart to collide with the two carts. Let's run this experiment again. So I've got the data going. I'm just going to pull my blue cart back to give it some acceleration, hold it still, and let's see what happens. So let's have a look at this data and see what we've got. Missed it, there we are. So it's going off with about 0.47 this time, and the other one is doing 0. Then we have our collision, and they're going off at 0.166, and we're seeing here the graph moving from 0 up there, and it stays at a constant velocity for the first little bit before gravity and friction start sort of competing here. But in our first little bit we can see that this is a straight line, and so we've got here this number. So let's have a look at what we've got. So if I look at before the collision, I've got basically the same as we had before. When we finish, if I say that these are literally 0.25 rather than what we had, which was 277, and that's going to multiply by our velocity, which I said was about 0.47. We can work out our collision before, and we know our mass of the other ones is also going to be 0.25. There's two of them, so it's 0.5 times 0. So that's going to disappear. We're just interested in that value. So let's go over to our calculator, and we've got 0.25 times 0.47, and that's giving me my momentum, which is surprisingly not very different than we had before, which is 0.1175. Afterwards we've got a mass of 0.75, and we're going to times that by our new velocity. Our new velocity, we can work out here, is about 0.167. And let's go off and do the calculations for this. So we've got our 0.75 times my 0.167, and that gives me about the same number. Within the realms of my masses that I have rounded, then we've got a number. If I wanted to be specific, I could work out what that number should have been. And instead of 750, that was actually 803. So if I want to go and try that out and get the right numbers, then we could have basically, I've lost my mouse, there we go, edited this out. And that's going to give me a worse number, 0.134. So the three of them up there from those values, pressing the wrong button, 0.134. And if we started this one at 0.277 times by 0.47, we might get a slightly different result. I'm not very hopeful of this being exactly right, but we've got about 0.13. So it did work really within the realms of my experimental accuracy. So we've got this idea of momentum, this idea of when one collides with two. How about one colliding with three? Yeah, well, we can try that one. Let's take my cart there. Did manage to press the button, which I didn't really want to do. One cannot put that one in at the top. There we are. Right, here we go. And we're going to do it with 3 carts. So let's see what happens. We'll set the recorder going. And we had barely any movement there. So it's sort of not very much there, but we can have a quick look and see what we've got. So looking at the figures here, I've got about 0.45 and it's coming out here. Those are the last figures. We'll see. Yes, it was about 0.1. So if we've got 0.4, it's then down at 0.1. We can see that again momentum is being conserved, and we've done then a series of experiments to work out what we've got. So we're looking at Newton's first law here, I suppose, that basically an object will continue or remain at rest unless it's acted upon by another force, and they stay the same there. Right, okay. Newton's second law, the rate of change of momentum of an object is proportional to the resultant force on it. And we can look at this way. So let me get rid of a sheet of paper. Not wanting to come. And if we write some of this down, we've got our force, and our force is going to be here, so like F, and this is going to be the change in momentum, which is going to be the final momentum minus the initial momentum divided by time. I can take the m out of here, and we know that acceleration equals v minus u over t, so therefore F equals mass times acceleration. That's quite nice, isn't it, how that all seems to work out. So we've got our initial speed and we've got our final speed, so we can actually work out what's going on. We can have our rates, so we can look at what's actually happening. So we've got our Newton's laws of types of reactions as they go, and this is equally true if we tried something like an air track. I don't have an air track. Seems an awful lot of expense for one little experiment, but the air track there would be a totally sort of frictionless environment and we get pretty accurate results. But if we use this track and what we do is we compensate gravity and friction, then we can get reasonable results with it. Let's have a look at another problem, and that's a problem of the man with the gun. Wrong button. Here is the man with the gun. Here's the gun. And here he is, ready to fire the gun. And the gun's got a large mass. Let's say it's going to have a mass of, it doesn't matter really, I can say 5 kilograms. Out of it is going to come a bullet, and the bullet, let's say, is going to have a mass of just 5 grams. Then if we work out our mass times our velocity, so this is going to be 0.005 times our velocity, maybe let's say 300 meters per second, then we know this is going to equal the 5 kilograms times the velocity we're going to have for this. Well, we can see that these are going to cancel out, so it's going to have here probably about a velocity here of just 3 meters or 0.3 meters per second. So this rifle is going to go back not very far, but it is going to go back a little bit because it's a much heavier mass. What we are seeing here in this sort of closed system is that we've basically got zero momentum. It's because they are cancelling each one out. This physics then can basically explain what goes on in a radioactive nucleus when it emits something like an alpha particle, and it can also explain how a firework will work. Now, we've met here an inelastic collision. I want to look at what will happen with this if we look at an elastic collision. So let's imagine we're going to look at this cart, and I'm just going to take the one cart for a minute, and what I'm going to do is I'm going to push this against this barrier. Now, last time when we had two things joined together, they basically, this one doesn't even touch, you see. When they touched, they joined together with this Velcro. Now what I'm going to do is I'm going to push these two together with this magnet, and I'm just going to have the red cart sink back down to me. We'll do it just with one to start with. So what's going to happen? I've got this cart, and it's going to have some zero energy in it. This one's going to be pushed, and it's going to collide with that one. What are your thoughts about what's going to happen? Well, let's try. And I don't know about you, but I still get a kick out of that one every time I see it. So this one lost its entire amount of energy, and it was transferred to the other one. We better see this in action. Hopefully the cart will stay where it is. Right, here we go. Next experiment, what we're going to do. I'm going to set this recording, and we're going to give this cart a push. And I thought I'd stop it just before we got there. Let's see what we had. This cart was moving. I'm just going to have to move it down a tad at about what, 0.7. So let's go and have a look at these values. There we are, about 0.7, and when it collides, the other one goes off with a value of about 0.6869. It does fall off quite quickly, but we've got here conservation of momentum. So the two collide, one loses all of its momentum, and it's passed on to the other one. Let's see what we can do with a bit more fun here. So taking the same idea, what we're going to do is collide it with not one, but this time two carts. What are your predictions this time when this cart hits that one? Here we go. Not what some people expect. This one, when it came in, it didn't lose all its momentum, but had some back because this had twice the mass. Let's see this one in action. So we'll start it up again. So we're recording. Let's see what happens with the carts. Let's give this one a push. And we can see that we started off with about 0.7, and it then came back with about -2, and this one came off with about 0.5, and if I add that one onto this one, we see that we came in with 0.7 and we go out with 0.7. Conservation of momentum. I'm never happy if I can't prove one of these things and see if it's going to apply for another cart. So let's try this. Let's increase this to 3 carts, 1 versus 3. We can imagine what's going to happen, but we'll see it first. Stay. There we go. Let's watch this. We'll reset this. Ready to go. Here's trucks going. That upset everyone by me moving it back. Here we go. And there is our resultant here. Thank you. I don't want to do that at the moment. So 0.8 here, about -4, and this one here getting on for -4 as well. If we consider that's not quite 8 and that's not quite, they're going to add up. So we can see that we've got conservation of momentum going here with elastic collisions and with inelastic collisions. So there we are. Simple bit of momentum and a few interesting experiments which are a little bit of fun to try and do. I hope you've enjoyed that. You might even be able to get some results from that. You can see my results on my screen, and I'll see you next time. If you liked this, please subscribe. Otherwise, I'll see you next week when we do some more A-level physics topic by topic. Bye bye.